All right, so let's look at section 10.3, calculus and polar coordinates. So just remember some the basic facts about polar coordinates. And polar coordinates, we have r and theta, which describe our point in space. Remember that x is r cosine theta, y is r sine theta, that x squared plus y squared is r squared, and the tangent of y over x is equal to theta. So these are the basic functions that connect our polar coordinates and our Cartesian coordinates. So our goal here is to start thinking about calculus. And so what's the first thing in calculus? Well, way back when we started calculus in Calc 1, the very first thing that you would have thought about is tangent lines. And so let's think about that in this situation as well. But what we're going to do, so when we started thinking about tangent lines in Calc 1, we had a function, f at x. Right? So f at x. So we're going to think about what we're going to call polar functions. So this won't be f at x, but rather something like, it'll be an f at theta. So theta is in fact going to be our variable here. And what does that mean? How are we supposed to think about this? We're supposed to think about if we vary theta. So this is some formula with thetas in it. So we're thinking about f at theta is as the radius. So as I change theta, so remember theta is moving around this circle counterclockwise. As I change theta, the radius is going to change. So as I move counterclockwise, I may get a different radius at different points. And so this, as we put this all together, so at this angle of theta, this distance here will be our f at theta. And that's the radius, the distance from the origin, as a function of that value of theta. So that's what we're doing when we think about this. So for example, just from some of the things that we saw from before, if f at theta is just 2, this means that the radius is 2 at all angles theta, so I have a circle of radius 2. If I had f at theta is theta, what does that mean? Well, that means that when I start at 0, if my angle is 0, my radius is 0, so I'm right down here at the origin. As I start moving around counterclockwise, the angle increases, therefore so does the radius, because r is f at theta, which is theta. So this is one that you should be okay with saying that in the end what we're going to get is a spiral shape. Because as I move around counterclockwise, the radius gets bigger and bigger and bigger. So this will create a spiral shape for us. So let's stick with that one that we have right now. F at theta is theta. And we can ask a natural calculus question. So here is the spiral. The radius is getting bigger and bigger and bigger as the angle goes all the way around. I can say something like, all right, well, what is, so suppose that this is this angle here, which is, so that will be pi. So this is angle theta is equal to 5 pi over 4. Because 4 pi over 4 is 1 pi, which is halfway around. So 5 pi over 4, if that's my angle, I want to know, what is this tangent line? That's our first goal. What is the tangent line to a polar function at some angle theta? So that's fine. Now, we'll be able to do that, and we'll come up with a formula that'll work in general, but this one is, the formula is a little bit messy, so it's hard to remember sometimes, and it's really best just to remember this. Really what we're looking for is dy dx. That's what gets me a slope of a tangent line. Dy dx is the slope of a tangent line. But remember that x is r cosine theta, and y is r sine theta. Okay, now we have to be careful because r and theta are related because we're starting with this function r is f of theta. So this is f of theta cosine theta, and this is f of theta sine theta. So if I want dy over dx, I can take the derivative of y, and I can take the derivative of x with respect to the angle theta, and then I can divide. Right, so we're going to think about this as dy d theta, take the derivative of y with respect to theta first, and what do we get? We get, this is a product rule, first times the derivative of the second plus the second times the derivative of the first. And similarly, dx d theta will be the first times the derivative of the second, which is minus sine, plus the second times the derivative of the first. So dy d theta and dx d theta we calculate, but the point is that dy dx is just dy d theta divided by dx d theta, because the d thetas cancel, and we end up with a formula that looks messy. It's hard to remember. In fact, you don't have to remember it if you just remember how we got it. And so let's go back and apply this formula to our specific situation that we started with. If f at theta was theta, then what do we need? Dy dx is f at theta, which is theta, times cosine theta, plus f prime at theta. Well, the derivative, if f at theta is theta, the derivative is just like the derivative of f at x equals x, which is 1. So plus 1 times sine theta, all divided by negative theta sine theta, plus f prime, in this case is still 1, times cosine theta. We were asked to find the tangent line of our function at a particular point, at the point 5 pi over 4. So at theta equal 5 pi over 4, we get 5 pi over 4. Cosine of 5 pi over 4, 5 pi over 4 is way down here. Cosine is the x, and so that's really a 45-degree angle down in there. So the cosine and the sine are both root 2 over 2, watching the sines. So the cosine is actually negative root 2 over 2, because that's a negative x, plus the sine of theta, which is, again, negative root 2 over 2. Divided by negative theta, which is negative 5 pi over 4, times sine of theta, which is negative root 2 over 2, plus 1 times cosine of theta, which is negative root 2 over 2. All right, so we have this negative root 2 over 2 here, negative root 2 over 2 here, negative root 2 over 2, negative root 2 over 2. You can think about factoring that negative root 2 over 2 all the way out. And if we did this in the numerator, we'd be left with a 5 pi over 4 plus 1. And then the denominator, we'd be left with negative 5 pi over 4 plus 1. The root 2's over 2's are going to cancel. And we can calculate this value. So we get 5 pi over 4 plus 1 over negative 5 pi over 4 plus 1. And we could do some algebra, but let's just get an approximation for what we've got. So 5 pi over 4 plus 1. Divided by that gives us about negative 1.68. 8. So this is our approximate slope of the tangent line. And notice it should be negative because for our spiral, at this point, we better have a negative slope tangent line. So what is this point? Now we want to come up with the actual tangent line in terms of x's and y's. Lines are tricky in polar coordinates, but we can write it in terms of y and x. This is the point. So this is theta was 5 pi over 4, and so therefore r was also f at theta, which is 5 pi over 4. So x is r cosine theta, and y is r sine theta. And so now I have x and y, so I have a point and I have a slope, and I could use our point slope form for an equation of a line to come up with the equation of the tangent line. So next we need to think about horizontal and vertical tangent lines. Remember that a tangent line is horizontal if dy dx is 0. But for us, dy dx is dy d theta over dx d theta. So I'm going to have a horizontal tangent line if this numerator is 0. But I can't have the denominator being 0, because if I have 0 over 0, that's something a little bit different. We'll see an example where we talk about how to deal with this. But so we need the top to be 0, but the bottom not to be 0. And that's going to give us a horizontal tangent line. A vertical tangent line will correspond to an undefined slope, but an undefined slope is when I have 0 in the denominator. So if I'm looking for a vertical tangent line, I'm looking for the denominator to be 0, which is dx d theta is 0, but I need the numerator to not be. Again, 0 over 0 is a special situation, and we'll see an example with that. But a vertical tangent line says the denominator is 0, but the top is not. So let's just apply these in our favorite example. So let's look at the polar function 2 plus sine theta. F of theta is 2 plus sine theta, and say, when does it have horizontal or vertical tangent lines? So we need to look at the numerator and the denominator in dy over dx. So we're looking at dy d theta, where remember the y is r, which is f of theta sine theta, so that the derivative is first times the derivative of the second plus the second times the derivative of the first. In this case, that becomes 2 plus sine theta times cosine theta, plus the derivative is cosine theta and times sine theta. Okay, now what does that make? That makes 2 cosine theta, and I have sine theta cosine theta and another sine theta cosine theta, so that's 2 sine theta cosine theta, which is 2 cosine theta times 1 plus sine theta. Remember, what we're asking is, when is this equal to 0? That's the numerator. So this is 0 when cosine theta is 0. And let's just say we're going around the circle one time from 0 to 2 pi. And since cosine is the x coordinate, that happens at 90 degrees or 270 degrees, which in radians is theta is equal to pi over 2, or else 3 pi over 2. That's when the x coordinate is 0 in the unit circle. This corresponds to sine theta is -1. But if sine theta is -1, sine theta is the y value. So when is the y value -1? Only at 3 pi over 2. But either of these things are okay, because even if theta is pi over 2, this portion becomes 0, so the whole thing is 0. All right, so these are our, so dy over d theta is 0 for theta equal pi over 2 and 3 pi over 2. What about dx? Dx d theta is, since x is f cosine theta, the derivative is the first times the derivative of the second, which is minus sine, plus the second times the derivative of the first. And since we're using this as our function, we get minus 2 plus sine theta times sine theta plus the derivative is cosine theta times cosine theta. And so this makes minus 2 sine theta minus sine squared theta plus cosine squared theta. Now this one gets a little tricky at this point, but just follow along and we'll see what happens. So I get minus 2 sine theta minus sine squared theta. I'm going to turn cosine into 1 minus sine squared theta, because cosine squared plus sine squared is 1. So I can turn cosine into this, and I can combine my like terms. If I combine the like terms, this equation becomes -2 sine squared theta, because I have a negative sine squared, minus 2 sine theta plus 1. Now, this looks like a mess. Remember, we're setting this equal to 0. That's our goal. Our goal is to set this equal to 0. But if I make a change of variables here, so suppose that I call this, if I let u equal sine theta, then this becomes -2u squared minus 2u plus 1 is 0. And that's just a quadratic function, a quadratic equation. And so we can either try to factor, or we can use the quadratic formula to say that u is -b plus or minus square root of b squared, which makes 4, minus 4 times 1 times minus 2, all over 2a. And so this gets me 2 plus or minus the square root of 4 plus 8, which is 12, over -2, which is 2 plus or minus, so 12 is 2 root 2 over -2, which is -1 plus or minus the square root of negative, so plus or minus the square root of 2. And so that gets me 2 values. But u is sine theta, right? So u is sine theta. So what we really then are looking for is sine theta is equal to -1 plus or minus the square root of 2. Now, it doesn't make sense to say minus, because if I put minus the root 2 in here, then -1 minus root 2 is -3 point something, and sine of theta is never that. However, it does make sense if I go the other direction. Suppose that I said sine theta is -1 plus the square root of 2. There is a solution to that. Theta will be sine inverse of -1 plus the square root of 2. Because the square root of 2 is 1.41 or something like that, and when I put this in, I get a number that's bigger than 1. Right? So, in fact, I'm going to have 2 values that work. Because if I have if I'm taking the sine inverse of a number that's positive, I'm saying when is the y value the positive version of this? There are two angles that'll work because I will have, if I suppose that I had if I want the y value to be this number, well, I'm going to have two angles that will work. One that's on this side of it and one that's on this side of it. So this actually gets me two values, but neither of them correspond to the thetas that we came up with over here. So at this point, I can say with confidence that these two values make the numerator 0 and the denominator not. So these correspond to horizontal tangent lines because the numerator is 0 and our dy over dx, but the bottom is not. Again, this is a bit more complicated, but there really are two values here. There really are two angles, this angle and this angle, for whatever you get here. And these two angles correspond to 0 in the denominator, but not in the numerator, which means that these things correspond to our vertical tangent lines. Calculus for polar coordinates, which is integration. So we talked about derivatives, tangent lines. Let's also talk about integration. So our goal here will be to do something very similar. We're going to ask to find an area, say, below a curve. But remember, so in Calc 1, if I had a function f at x, and I said find the area below the curve from a to b, we'd integrate from a to b of f at x dx. That's what we did with the area below the curve. The problem is that now when we have an r equals f at theta, it doesn't look like this anymore. Because when I graph it, the function is not a function above the x-axis anymore. It's a function that goes something like this. Right? So as theta changes, r changes. So now when I say below, I can't be bounded by a and b on the x-axis. What we can be bounded by are theta 1 and theta 2. Right, so we had an x1 and an x2 up here when we integrated f at x. So now let's have a theta 1 and let's have a theta 2. Two angles which bound some region. And now when I say below, when I meant below up here, I don't mean below in the same sense. I mean before somehow or another, right? I mean this thing that looks a bit like a piece of a pie. And that's what we'll be asking for when we say integration in polar coordinates. We want to know, what is this area? All right, now we need a little bit of background before we develop the main tool that we'll use in this situation. The idea here is as follows. When in Calc 1, when we did this, when we found the area below the curve, we broke things up into small little pieces, a bunch of different rectangles. We had a bunch of different rectangles, each of length delta x. Remember that. Right? So each of these rectangles was of length delta x, and the height was f at x sub I, where x sub I is, say, the left-hand endpoint of all of those rectangles. And then we made a Riemann sum. I'm not going to worry about going through this in complete detail, but a Riemann sum was the height times the length, and then we added them all up. And so this was from I equals 0 to just n minus 1, because I'm only looking at the left-hand side, and if I went all the way to n, then we would have included the far right one, which is no good here. So that's what we did in Calc 1. And the trick here is that when I multiply these things, this gets me the area of the rectangle. So I added up a whole bunch of areas of rectangles, and I could simply multiply f at x times dx because the area of a rectangle is just the base times the height. It's a bit more complicated now in this polar situation because now we've got our function, which is out here. We've got these theta 1 and theta 2, which bound things. And so what's happening when we break things up in, we're not going to use rectangles anymore. That's the first thing. When we break things up into small pieces, we're going to think about moving from from theta 1 to theta 2. In the Calc 1 situation, we move from x1 to x2 by jumping. So if I go from theta 1 to theta 2 and I jump, so I'm going to jump like this, what I get is not rectangles anymore, but these small things that look like pieces of a pie. So there's no rectangles anymore. No rectangles. But instead, this type of shape here. That's what we're looking at. So what we need to know is, what is the area of one of these things? Right, so let's say that this is at angle theta, and at radius f at theta. Because the f at theta tells me the radius. So if I have a particular angle theta, and I have a particular f at theta, and this length in here will be our delta theta, how much we jump each step. This is a kind of a long process, and in the end we're going to get to a formula that we just have to practice using. I'm not going to test you on all of this Riemann sum stuff, but this is just if you're interested and you want to get some idea about how we get to this final formula. And so this is how it goes. So we're looking at this picture. We're looking at a piece of a pie, and we're going to say that this distance, or the change in the angle, is d theta. We're going to say that this distance down here is r, and we want to know how much area does this whole piece of the entire circle actually contain. So let's think about it in a few ways. So first, notice that the area of the entire circle is pi r squared. The portion of the circle that we have is delta theta divided by the entire theta. So the percentage of the circle that we're actually using is delta theta divided by the entire possible theta, which is 2 theta, all the way around. So the entire circle is this area, but we're only using this portion, so the area that we have is actually the portion times the total area. So delta theta over 2 pi times pi r squared, which is, the pi's cancel, and we get r squared over 2 delta theta. Remember where this came from. This came from our bigger picture, where we actually had a theta 1, a theta 2. We had a function, r equals f at theta, and then this was our d theta in here, our delta theta here. So r really was f at theta, and so I'm going to think about this as f at theta squared over 2 delta theta. That's the area of an approximating piece when we calculate the total area. Again, it's a funnier formula than just f at x dx. F at x dx comes from base times height. We have a different formula because it's not just a rectangle, it's a sector, this piece of a circle. And so we have a more complicated formula. The Riemann sum then would be the sum of the area of the approximating pieces from 0 to n minus 1 as before. But when we take a limit and turn it into an integral, there's not too much different. We're going to take the integral from theta 1 to theta 2 of the function f at theta squared over 2 times d theta. And this, in the end, is the formula that we need to remember and know how to use. We're going to look at some examples and how we actually apply it. But all that work that we did really just got us to this point. You'd have no idea probably at all where this is coming from if we just throw it up on the board. That's what's happening. We're thinking about approximating areas by pieces of a pie, And by doing so, we end up with this formula. So let's go ahead and apply that to a couple of examples and take it from there. Then r, f of theta is cosine theta. I'm going to do a little bit of algebra here. I'm going to multiply both sides by r. I get r squared is r cosine theta. But r cosine theta is x. And r squared is x squared plus y squared. So I get x squared plus y squared is x, which says that x squared minus x plus y squared is 0. So if I complete the square on x squared minus x, this becomes x squared minus x plus 1/4. And if I put a quarter here, I better put a quarter here. Again, you don't have to really remember this. I'm just doing some algebra so we can understand what this graph is. I got that quarter from taking 1/2 of the coefficient of x and then squaring it. And the point here is that then this becomes x squared minus x minus 1/2 quantity squared. Because if I square this, I get x squared minus 1/2 x minus 1/2 x makes minus x, and 1/2 times 1/2 makes 1/4. And the point here is that this is an equation of a circle. This is like x squared plus y squared equals r squared. So it's a circle, but I've just shifted in the x direction, and that's what completing the square gets me. So this is actually a circle. It's a circle that's no longer centered at 0, 0. It's centered at 1/2 0. And its radius is the square root of a quarter, which is 1/2. So we've got a circle that's shifted over that direction. Where does it start? If theta is 0, cosine of 0 is 1, which means it starts right here. So we started right here. Now, so how am I going to make the upper half of this circle? Well, if I go from theta equals 0 all the way around to, so this point actually corresponds to theta equals pi over 2. When we got up to pi over 2, the cosine of pi over 2 is 0. So by moving our angle up, the radius is actually coming down back towards 0. So this region here is theta equals 0 to pi over 2. We know what the area of a circle is, so we should be able to come up with the area of this half of a circle using our formula. Let's just make sure that it matches. Right, so what is that area? That should be the integral from 0 to pi over 2 of the function squared, cosine squared theta over 2 d theta. Now, this is something that we haven't done for a little while, but we did actually talk about how we can integrate, how we can find an antiderivative of cosine squared. Remember our double and our half angle formulas. Remember that cosine squared theta was 1 plus cosine 2 theta over 2, which I can then use to rewrite this as 0 to pi over 2. Cosine squared is this. We still have the 2 that's in the denominator. Let's bring that all out as a quarter. 1 plus cosine 2 theta. Integrate becomes 1/4. If I integrate 1, I get theta. If I integrate cosine 2 theta, I get sine 2 theta, but divided by 2 because of the chain rule. And then evaluate it from 0 to pi over 2. When I plug pi over 2 in, well, when I plug 0 in, I'm going to get a 0 here and a 0 here, so everything is just 0. When I plug pi over 2 in, I get 1/4 times pi over 2. Sine of pi over 2, sine of 2 pi over 2 is sine of pi. Sine of pi is halfway around the circle. Sine is y value, so that's actually 0. So this is what I get. I get pi over 2 times 1/4, which is pi over 8. But remember, this was the circle with centered here, but the radius was 1/2. So if the radius is 1/2, the area is pi r squared, which is pi times 1/2 squared, which is pi over 4. That would be the area of the entire circle. If I wanted just the area of half the circle, I'd have to divide by 2, and I'd get pi over 8, just like we did here. So I use that as an example of looking at some algebra that allows us to go back and forth between the way that a function looks like in polar coordinates and what it might look like in the xy coordinates, and just give you some evidence that the formula that we came up with actually is correct and does work. Okay, and so that's what we got from this section. Check out the homework.